All right, describe the end behavior of f. What the end behavior is, and you may remember this from last year, is that what we say is as x approaches infinity, f of x is approaching what? 2. Very good. And then the other half of the end behavior is as x approaches negative infinity, f of x is approaching negative 2. What characteristics of the graph do we have going on here that aren't really shown? Good. We have some horizontal asymptotes. And this may be the first time that you've seen a graph with 2 horizontal asymptotes. All right, so a horizontal asymptote, the formal definition, we talked about them last year, but the formal definition involves calculus and limits. The line y equals L is a horizontal asymptote of the graph of f if the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. So as long as x is approaching positive or negative infinity, and the limit is a specific number, then that means that you have a horizontal asymptote. And if you recall, there are some rules for horizontal asymptotes, so let's talk about them. F of x actually approaches 2, thank you. Negative 2. All right, so we're going to let f of x be a rational function. Rational means fraction, such that f of x equals g of x divided by h of x. If the degree of g of x is less than the degree of h of x, so if the degree of the top is less than the degree of the bottom, then you would have a horizontal asymptote at y equals what? 0. And therefore, the limit as x approaches infinity of f of x would equal 0. Horizontal asymptotes and limits as x approaches infinity or negative infinity are going to be the exact same thing. Because that's what a horizontal asymptote does, is it guides the graph as x approaches infinity or negative infinity. Okay, if the degree of g of x equals h of x, so if the degree of the top equals the degree of the bottom, who remembers what the horizontal asymptote would be? The ratio of leading coefficients. Very good. So the limit as x approaches infinity of f of x would equal the ratio of leading coefficients. For the most part, you need to memorize them. However, it does kind of make sense from a limit, now that you know limits, and I'll point it out to you as soon as we have some specific examples. All right, what happens if the degree of g of x is greater than the degree of h of x? What type of asymptote do you have? A slant asymptote. Thank you. All right, now, if we have a slant asymptote, let's say like this. Yeah, the solid line's the y-axis. And then I have a slant asymptote that's going up like this. As x is approaching infinity, what is f of x approaching? Also infinity. Okay. So the degree of the top is less than the degree of the bottom. The limit will be 0. The degree of the top equals the degree of the bottom. Your limit's the ratio of leading coefficients. And if the degree of the top is greater than the degree of the bottom, your limit is infinity. So let's find some limits. All right, A, limit as x approaches infinity. 3x minus 7 over 2x squared plus 1.
0.
It's 0. Good. Degree of the top is less than the degree of the bottom. You're done. That's all you have to do. Okay, now let's think about why this limit is 0. Is the top or the bottom getting bigger faster? The bottom. So you're taking kind of a big number, but you're dividing it by something that's getting bigger and bigger and bigger faster. So if you have a big number divided by an even bigger, bigger, bigger number, that's going to start approaching 0 or a fraction, and then eventually go to 0. Okay, what's the limit as x approaches infinity for b? Negative 5 halves. And for c? Infinity. For now, you don't have to do the long division, but in just a minute, I'm going to ask you to do a little bit of long division. But if it just asks for the limit, okay, here's the difference. If it asks for the limit as x approaches infinity and the degree of the top is greater than the degree of the bottom, it's infinity. But if it asks for the equation of the asymptote, you're going to have to do long division, which we'll practice in just a second. Okay, someone said, will you explain to me why b is negative 5 halves?
No, I know. I understand, like,
Okay, if you think of, what I want you to do is I want you to divide every single term by the highest exponent, which would be x squared. So we would have negative 5x squared over x squared plus 7 over x squared, and then 2x squared over x squared plus 3x over x squared minus 1 over x squared. And it's okay to do that because I've done the exact same thing to every single term in that equation. Well, the limit as x approaches infinity, well, okay, if you reduce this, then you get negative 5 plus 7 over x squared over 2 plus 3 over x minus 1 over x squared. And now if you take the limit as x approaches infinity, 7 over infinity cancels out to 0. 3 over infinity approaches 0. 1 over infinity approaches 0. And you're just left with negative 5 halves. You're not technically dividing 1 by infinity, but you're dividing 1 by a bigger and bigger and bigger number. It's like 1 divided by 100, and then 1 divided by 1,000, 1 divided by 1,000,000. Those numbers are approaching 0. Okay, the graph of a rational function approaches the same horizontal asymptote from both the left and the right. That's what you were used to seeing last year in pre-cal, that you just had one horizontal asymptote. However, there's some functions that are not rational and may approach different horizontal asymptotes to the left and the right, meaning that as x approaches infinity, you may be approaching one number, and as x approaches negative infinity, you might be approaching another one, which is what happened on the very first example on this page up here. You actually have two horizontal asymptotes, which is fine. Okay, so determine the limits. Is this as x approaches positive infinity? Yeah, okay. What's the degree of the top? 1. What's the degree of the bottom? Well, your highest exponent is x squared, but you're taking the square root of it. So the degree of the bottom is also 1. So the degree of the top and the degree of the bottom are both 1, so therefore the limit should be the ratio of leading coefficients, which would be what? 3 over root 2. Very good. Okay, because that 2 is under a square root. All right, now we've got the exact same problem, but this time the limit as x approaches negative infinity. Riley? Okay, does the plus or minus for root 2 apply? No. If you have a problem that's already part of, if a square root is part of the problem, so like if the square root of 4 is the problem, the square root of 4 is just 2. The symbol square root means take the principal or the positive root. So if the square root is already part of a problem, you don't do plus or minus. But if you have x squared equals 4 and you have to take the square root of both sides, that's when you have to do plus or minus. If you introduce the square root, it's plus or minus. If the square root's already there, it's just plus. Good question. Okay, B is the exact same problem, except this time it's as x approaches negative infinity. Well, it's going to have something to do with 3 halves. But on top, as x approaches infinity, am I going to get a positive or a negative number on top? As x approaches negative infinity, is the numerator going to be positive or negative? Negative. And as x approaches negative infinity, will the denominator be positive or negative? Positive. So therefore, the limit is negative 3 over root 2. We didn't really think about it in part A, but in part A, as x approaches positive infinity, 3 times a positive infinity minus 2 is a positive number. And then the bottom, since I'm squaring x, will always be positive. So I had a positive divided by a positive, which would be positive root 3 over 2. But x is approaching infinity. It doesn't really matter what's happening around 0. It's just as x approaches infinity or approaches negative infinity. Yep.
You don't have to do this thing where you make the negative square root or radical on top.
No, you do not have to rationalize the denominator. Okay, trig limits. The limit as x approaches infinity of sine x. As x approaches infinity, what is the sine of x doing? It's oscillating between what and what? 1 and negative 1. So what can you tell me about that limit? Does not exist. Well, the graph of sine x looks like this. And I wouldn't, whoops, I didn't really mean to draw that horizontal line. I wouldn't say that there are two horizontal asymptotes, but you just keep fluctuating between a high point and a low point. Mm-hmm. No, it's not wildly oscillating. It's just oscillating. Yeah. Right. It's because your y values are not approaching one specific number. They keep going back and forth between positive 1 and negative 1. Okay, Gray, are you already talking about part B? Oh. Good. No, I'm glad. Have you come to a conclusion of what this limit is? It is. It's 0. Why? Okay. The top is oscillating between negative 1 and positive 1. You okay with that? But then as x gets bigger and bigger and bigger, you're dividing by a bigger and bigger and bigger number. So you basically have something between negative 1 and positive 1 divided by infinity. So even though the top is going back and forth between 1 and negative 1, your bottom is getting bigger and bigger and bigger, and it's going to approach 0. What the graph of this looks like is this, where you're still going to be oscillating between 1 and negative 1, but every time x gets bigger and bigger and bigger, that oscillation is getting smaller and smaller and smaller and getting closer and closer to 0. Kelly?
So wouldn't it still be going, above and below?
It is still going above and below 0, but each time it gets closer, it gets not as far away from 0. And so, but it's still it's the whole concept of approaching 0.
Since that one was like set 1 negative.
Right. The previous one was literally just going up to 1, down to negative 1, up to 1, down to negative 1, and forever and ever and ever 1 and negative 1. But the next one, it's switching positive and negative, but as it's switching positive and negative, it's decreasing and getting closer and closer to 0.